Hello everybody, thank you for being here. So I'm very happy to welcome today for the Public Health Seminar Michael ELIOTT, who is a professor of biostatistics at the University of Michigan and a research scientist at the Institute of Social Research. His main interests are in the design and analysis of complex data coming from surveys and population-based cohorts, with interest in missing data, causal inference, and modeling of the mean and the variance. So we welcome him today and for the week. You will have this seminar today, another seminar on surrogacy on Thursday, if you are interested, and there is also an open class on Friday morning from 9 to 12, open to everybody. We will be in the Amphitheatre 1, so a big place so that you can come. It's on invitation. So thank you very much, and Michael, and the floor is yours.
Well, first I want to thank very much Dr. Proslima for inviting me, and for everyone here who's been hosting me. It's been wonderful. People have been very friendly and nice. It's great to be traveling again and meeting people and talking and having the kind of conversations that we were all missing, I think, for the last year and a half. I also want to apologize in advance for my profound lack of French skills. I made choices about how to spend my time in life, and now that's one I regret, not boning up more on that. But I'll do my best, and hopefully we'll work together here. So my talk today is all of my talks are going to, I'm a biostatistician, so there's going to be some mathematical components to what I'm talking about, but I'll try to, and Greek letters and things like that, but I'll try to minimize minimize that to the extent that I can and try to sort of focus on some conceptual ideas as well. So what I'm going to talk about today is really this idea of using variability in longitudinal data as a predictor itself. So in settings where, well, first of all, I should mention, I want to thank a number of my fellow faculty at Michigan, some students at Michigan and now elsewhere since they've graduated, and a couple of grants that have supported a portion of this work from NIH. So there's this idea that we certainly use longitudinal data quite a bit in our lives. A lot of the focus has been on mean trends or profiles, sort of treating correlations as nuisance parameters. So if you're going to analyze a data set where you have multiple observations from an individual measured over time, you often may use things like generalized estimating equations or random effects models to try and account for that correlation. But your main focus is usually on some direct association between a variable value at one point in time with the expectation of an outcome at that level. So what I'm going to do is kind of sort of turn this around a little bit, or at least add to this by thinking about the possibility that subject level variability itself can provide information in addition to the sort of mean trends. So there's some examples of this from the data, from the literature going back up to 20 years, much of it in the women's health field. So a couple examples here looking at associations between menstrual cycle and age. And actually, it turns out that when looking at the onset of menopause, that the first sort of predictor that you can get of this is increase in variability in menstrual cycles. So they sort of average, 28 or 26 or 29 day level for a given woman may sort of stay pretty similar, but suddenly it'll become more unstable month to month. Also in other areas, blood pressure, particularly in cardiovascular health, I think concerns about variability in various biometric measures has been shown to be predictors of increased cardiovascular risk. So I'm going to start off with a motivating example that goes back quite a ways now, from early part of my sort of postgraduate career, when I was asked to look at some data that evaluated persons' moods. So these would be sort of short-term daily measures of how you're doing. Do you feel you have a happy mood? Do you feel you have a sad mood? And there's somewhat independent scales from each other so that you could think of people having sort of potentially high levels on both for a given day. So these so-called affect scores were recorded by daily diary for up to about a month from 35 patients recovering from heart attacks, myocardial infarctions. And so the actual data, if you look at it, you can kind of see there's sort of an interesting issue in the variability of the variability. So some individuals, like this individual, tends to be quite stable with a few outlying trends. This one's more variable. This person's highly variable and seems to have some sort of shift in positive affect kind of going up over time. So it occurred to me that maybe looking at variability should be something we should think about here. Now, of course, variability is linked to estimation of trend, right? If you essentially just look at the standard deviation for an individual set of measures over a period of time, that assumes no trend. You're just sort of subtracting things from the overall mean. You could, of course, sort of interpolate a trend at observed values, which would assume no variation, right? Your point estimate at that point is the actual value. So, so for this particular analysis, thought about removing the trend using sort of a non-parametric spline. I don't know. Again, there's probably some heterogeneity in people's background here, but this is basically a way to kind of fit a regression model, but not one that assumes linearity or even a specific quadratic or cubic trend. It can be a little bit smoother. So you can actually see that some of these have been fit here, right? So here our spline gives something very akin to a linear model. Here it gives something that's a bit more is obviously not non-linear, kind of tracks up there. So, and specifically, we had this idea of this idea of using a model which sort of starts with looking at a mean square error function and then penalizing how wiggly that function is. So this is a second derivative of that function. So if the sort of more shifts and changes, the larger this value is here. You can shrink this by making it sort of wigglier, but you also pay a price here. And this lambda I is sort of a penalty measure that just sort of tries to decide how large that price should be. So it turns out you can use a sort of correspondence between this sort of infinite dimension model and a finite dimension linear model. It converts this into something that looks like a linear model where the variance, the random effect variance is a function of the individual variance divided by this penalty parameter, and then everything else is basically parameterized by this simple linear fixed effect piece. So the main focus we're going to have here is on this sigma I. Right, we're sort of trying to decide, is this sigma I, this residual variance, predictive of an outcome, in this case, minor depression at the end of 35 days. And without getting too buried down in the weeds here, we fit a hierarchical model, a latent class model. So we're going to see this idea of latent classes coming up again and again in this talk. So we're basically saying that conditional on being a member of some latent class here, then this residual variance follows this inverse chi-square distribution, where the parameterization of the inverse chi-square is a function of the latent class. And then we have this latent class can be a function of other covariates. And we had very limited data here, so I sort of fit 3 separate models using depression, gender, or elderly status as a predictor of latent class. So some more details. We used an EM type algorithm to fit this, used bootstrapping to get inference, and then we used a sort of an extension of BIC, a way of sort of looking at the model fit, because we don't know really the number of classes, right? This could be 2, 3, 4, 5 classes. So we tried to find the best model fit using this idea of BIC, sort of an extension of BIC criteria, if you're familiar with those. So the bottom line in this is that sort of depended on exactly which predictor we were putting in, but we generally found 3 classes. They sort of centered around a low variance class, a middle variance class, and a high variance class. Interestingly, if you take the square roots of these, you get 1, approximately 2, and approximately 3. And these scales in the end were integer valued. So even though I'm treating this as a normal distribution, sort of granularity probably comes out there a bit. And so the sort of intermediate class sort of struck out as being, sort of popped out as being the highest risk of depression. They were slightly more male, a little bit older, but that was probably the only thing we found that was significant. To some extent, this is sort of a proof of concept more than a serious analysis, given the limited number of observations. But it did suggest that there might be something going on here with variability. So, okay, so I want to move on to another motivating example. Sort of monitoring variability as a predictor of health outcomes here. And this is, we're going to take this from the idea of trying to decide, do measures of memory tests and cognitive tests predict transition to dementia? I know I've had some conversations here yesterday that I know at least some of you are working on this area. So we used data from the Health and Retirement Study, which is a large U.S. survey of persons 50 years and older, and have been followed for about 16 years at this point in time. And each time, every 2 years, they're given questions about sort of short-term memory tests, and then also some questions that kind of can do an approximate diagnosis of dementia onset. So again, this idea of sort of, now we're going to try to build in the mean trend itself as well as the variance. So we think maybe there's something about the changes in these cognitive measures, overall, the mean levels, as well as sort of the year to year, I guess every other year to every other year measure of variability, right? Sort of residual short-term change. So we're going to use what's termed a shared parameter model. So we're going to have our mean trend for the Y's, which are these memory tests, going to follow some mean that's characterized by these subject level beta parameters, and then there's a subject level variance, and then the outcome is going to be a function of the subject level means and variances, as well as possible fixed effect covariates. And I'm going to kind of use a logistic regression for that piece. And then we're going to sort of smooth across these. We're going to allow for some information to be shared across individuals by using a normal prior distribution on these mean trends, and now a log normal. I use the inverse chi-square. Both of those are sort of logical parametric ways to think about doing this smoothie. And we can have some discussion about which one of those might be best or other alternatives. But for right now in this analysis, that's what I did. And again, the focus is on these parameters are going to affect this outcome in a continuous manner. So I could, in theory, fit this via EM or numerical integration, but in practice, these methods proved really computationally intensive and also kind of unstable. So instead, we used a fully Bayesian approach. I don't know how many folks are familiar with Bayesian type approaches here. I'm not going to get into the details. But right now, you can think of it as an alternative way to kind of deal with the numerical process of trying to get inference about these parameters that we're interested in, which ultimately, I guess maybe I should go back. Ultimately, they're going to be, functions the sort of mean parameter for the function of this probability of onset of senility. So again, to kind of get into the actual example here, these Ys, these longitudinal measures of recall were essentially 10 words of immediate recall and 10 words of delayed recall. So you get, if you've had an elderly relative that's had one of these tests, you may have seen how these work. You have this very quick immediate recall, and then there's a little conversation, and you're asked about words that you were maybe told about several minutes ago. And then our outcome is going to be presence of dementia. So this is starting with persons who have no presence of dementia at the time of the initial baseline interview, and we then did restricted to individuals that had at least four follow-up interviews. And about a quarter of the subject had a dementia diagnosis after 16 years. So the idea being that that the investigators that suggested this were concerned that variable cognitive performance might sort of precede consistently poor performance. So not unrelated to the very first example I mentioned, where variability in menstrual cycles sort of is an earlier indicator than the mean for the cessation of menstruation, and here this would be for the onset of cognitive impairment. So just a very little simple preliminary analysis, just little spaghetti plots amongst patients who did and did not develop dementia. It's hard to see a lot going on here. You might, maybe a bit of a trick of an eye, see some more decline in the dementia patients, and maybe a bit more variability. It's a little hard to tell from that little example. So of course we're going to go on. I'm sorry, this is a little bit of a busy slide here. I'll spend a minute kind of working my way through it. So we're going to start off with our mean model for the data, basically just a quadratic model on age. So we're going to have an intercept, a slope, and then a curvature parameter that's going to allow for potentially quadratic effects or linear effects or even just stability over time. We sort of standardize age to have a mean of 0 and a variance of 1 to improve convergence here. And that's the key part for the outcome model. We're going to allow these intercept, slope, and curvature, as well as the variance to play a role in the probability of onset of dementia. It turned out it was kind of very nonlinear in this variance, so we have a sort of a little restricted cubic spline that allows for variance to have a nonlinear impact on this risk. And then we adjusted for a bunch of covariates that are even there. So, okay. So then the outcome, basically what I've done here is plot the predicted, the log odds of dementia, try to make, I could give you the coefficients, but those would be a little harder to interpret. So what I've done here is plot the log odds of dementia relative to the overall mean for whatever the overall population mean was for subject level intercept, subject level slope, subject level curvature, and subject level variance. These little tick marks are the beta i's or the sigma squared i's, or I guess the sigma squared i's for each individual in the sample, or also for a random sample, maybe 100 from the whole 8,000. So you can see that really there's only 2 that were technically significant. There's some evidence that higher level intercepts were associated with increased level of dementia, and that whereas slopes, sort of more positive slopes were at lower risk, which makes some sense, right? So actually higher level intercepts is a little, even though I guess these are sort of centered, it's a little hard to say exactly. That would actually maybe be somewhat counterintuitive, although the result is not quite significant. Obviously the more rapid declines in slopes, you might think would be a higher level of risk, but here there really wasn't much, particularly since we're including variance. Curvature, So this is sort of the rate of the drop. Higher curvatures were, or less negative curvatures were associated with increased risk of dementia, and increased variability, at least up to some larger value, was also associated with increased risk of dementia. So really it seems like the sort of variance is, again, the thing that's kind of popping out as most predictive here. It actually seems to be more important than the mean trend itself, at least for this early onset. So we also compared this with a two-stage model. So this is going to kind of get at my next point I wanted to get at here, which is that if we just take each individual and fit that same linear model, just a quadratic trend in age, we get an estimate of the slope, intercept, and the curvature from that individual fit. We then take the resulting residuals, compute residual variance right after you've taken out the curve. And if we just put those four things in and adjust them, put them in to the two-stage model, you put them into the outcome model, these are the coefficients that you get. Whereas our joint model that I showed on the previous slide, these are the coefficients associated with that. So these are, as I said, these are a little hard to interpret, but the bottom line here is you can see the effects are much stronger in the joint model than in the two-stage model. So this suggests that measurement error, right? It's very important to be using this multi-stage model in a joint fashion, rather than kind of this sort of more ad hoc two-stage approach. To get anything close to what the truth is. And we then showed that in a simulation study. So here we just had generated some individual level linear trends for our outcome, and then had just linear trends for our predictors, and then had our outcome be a function of slopes, intercepts, and variances. We tend to have fairly strong effects here, and for an outcome that's not extremely common, but not uncommon either. So you can see the two-stage model. So there's no overall mean here. So these parameters don't really have a mean in a two-stage model. And if you look at the bias in the resulting parameters, you can see this idea sort of bias toward the null that you see in measurement error, right? So the true value for gamma 1, gamma 3 were both positive, but the resulting estimators were still positive, but much smaller, negatively biased. This was actually set to have no effect. The resulting bias problems here led this to be biased upward, and you can consequently see coverage is basically close to zero, and there's a lot of times where we detect an effect here where we shouldn't have one. Whereas when we fit it with our joint model, we can see we got good nominal coverage, limited bias, and the power was the way we expected, right? You're seeing the effects that are real and not the effects that are not. So that suggests that the result we saw here is indeed reflective of measurement error, and that we should trust these results a lot more than these results. Okay. So I think I kind of summarized this before. The sort of increased mean level and increased quadratic trend associated with increased risk of dementia onset, but the residual variability was the thing that really was a little more striking. The low variability was associated with lower risk, and high variability associated with higher risk. So the mean trends themselves were weak, and they were kind of a little reversed from what we hypothesized. That maybe there was a sort of a strong correlation amongst the intercepts and curvatures that led to some instability and associated effects. But in any event, they seem to be relatively weak effects, whereas the variance was a little bit stronger. Okay. So So I want to go on a little bit here and do another motivated example, somewhat similar to the previous example, but here I'm going to be using this idea of latent classes rather than shared random effects to look at the joint modeling. So, and we're going to be moving now to this women's health world. We're particularly looking at variability in estradiol, whether it predicts some symptoms of menopause, in this case, kind of severe hot flashes. So we start out with a fairly similar model for the outcome that we had before. So we have for the predictors we had before, so we have some predictors here that are a function of subject level mean trends and variance. But the second stage of the model we're going to do a little bit differently. We're going to assume that those mean trends follow some normal distribution, but it's not just a common normal distribution now. Right? We're going to be allowing for more of a mixture of normal distributions. And similarly for the variance, a mixture of normal distributions for that. So these DI and CI are defining these latent classes of longitudinal mean and variance cluster memberships. And that's what we're going to be using then to focus on our outcome. Our outcome, we're going to actually use more of a probit type model. We could use logistic regression here, but there are some things that, in a model this complicated, the probit was a little easier to deal with. And basically the sort of transform probability of the outcome is now going to be a function of these latent classes. It could be just the main effects of the classes, could be interactions between them. But that's the main point. You can also put in adjustment covariates as usually is the case. So again, in theory, we could use EM or numerical integration, but the Bayesian approach seemed to be more doable. So the actual analysis, 436 women, sort of in early midlife, were then followed with up to 3 assessments a year for 8 years. And we're trying to understand how, and I guess I errored the slides. I said estradiol before was actually follicle stimulating hormone that we analyzed. So we restricted the women that, again, had no symptoms at baseline and had at least 4 measurements of FSH and follow-up. So the actual trend, so if you've sort of worked in this area, you know that follicle stimulating hormone tends to increase around the time of menopause. So we did a little trick here because this is quite nonlinear. Again, it's really variability in trends and variability in variance itself that we're focused on. So the overall trend is kind of a nuisance. So we just used like a low S curve to kind of take out the overall predicted mean. And what we were left with had that kind of a distribution marginally. And our best fit model, we used DIC again. It seemed that a linear model for the FSH detrended was enough. But we didn't really seem to have any variability in the health class in the means themselves. These intercepts and slopes all seem to come from a common bivariate normal distribution. That was not true for variance. Clearly, there were 2 different bimodal components to variance, and we, of course, without just one main trend, it would be hard to get interactions. So the actual predictors. So these little gray lines are individual level estimates of these B naughts and B1s, and then the overall mean trend for the center of the beta naught and beta 1 by age. For variance, we found these 2 classes. One is this sort of high variance, the sort of normal, sort of higher variance class, and then there was evidence of sort of a lower variance class here. So when we plug this into our probit model, adjusting for weight and smoking, we did see some evidence that this higher variance class had an increased risk of hot flash. So quite a bit, quite substantial and quite significant. So turn around the other way, you could think about the 1 in 5 women belonging to a low residual variance class having a greatly reduced risk of hot flash. So we did a little simulation study on this to, again, sort of see if our model was working and give some evidence of how well things to be distinguished. In particular, with this latent class idea and this mixture situation, you may have situations where the mixture components overlap quite a bit, and so that would be hard to distinguish those classes, and other situations where they're well distinguished. So that's what we wanted to consider, kind of a moderate sample size, 1/3 belonging to the first class and 2/3 belonging to the second class. And then, hopefully you can see this. All right, so the colors were so-so. So the yellow is sort of class 1 and the blue is class 2. So the first situation, there's quite a bit of overlap. So the slopes and intercepts for class 2 are coming in this range, and for class 1 are in this range. And similarly, the variances are kind of here and then here for the first and second classes. Second class, we now have well-distinguished means, but the variances are the same as in the first scenario. Third scenario, now the variances are well-distinguished, but the means kind of follow the first scenario. And then the fourth scenario, both the means and the variances are well separated. So, and then we're going to fit a model for an outcome that allows for an interaction. So these, 1 is for the mean, 2 is for the variance, 3 is for the interaction. So the bias and coverage here. So I'm looking now just at the mean model, at the predictor models. When neither were well separated, maybe not surprisingly, we had a fair amount of bias, particularly in the second for the second distribution. Even though the variances were not well separated, the bias here was quite a bit smaller. When the means were separated, we kind of get rid of that bias. In the intercepts and slopes, the variances were even better here. When the variances were separated, again, fine, not surprisingly. The mean biases were a little bit reduced. Now the variances were working well, but still somewhat overlapping. And finally, when everything was well separated, everything looked great. So in some cases, many cases, the coverages were not bad. You really had to have substantial bias to kind of blow up the coverage. But it does indicate that these latent class models are going to be somewhat susceptible to situations where the classes are not well separated. In terms of the longitudinal component. However, when you went to what we're really after in the end, I think, which is the sort of effect on the outcome, things looked a little bit better. Still had some substantial bias when things were well mixed. Coverage was not terrible. The bias was greatly reduced when at least the variances were well separated. Kind of when the means were well separated. When the variances were well separated and the means weren't, that bias kind of crept back in. And of course, when everything was well separated, it worked well. So the susceptibility kind of remains there. Maybe not so much on coverage, but on bias for the outcome. So, again, to kind of move back and summarize this example, the sort of stable FSH with low variability is consistent with premenopause reproductive function, where we expect low rates of hot flashes. Other research has demonstrated increased risks of hot flashes with increased levels. And here we didn't really see clustering of mean trends. I didn't show you, but we also fit a shared random effect model similar to what I showed you with the HRS and dementia example. that showed positive associations between slope and hot flash risk, which were consistent with what we, which was consistent with the previous literature, but they were very marginal. They were not quite even statistically significant. But the demonstration that women have with low intra-subject variability, a much lower risk, was consistent actually in both the latent class and the shared random effect model. Okay. So I have one last little example I want to go through here. It's not little, but it sort of is, you think of this as sort of maybe a bit of an orchestral piece here where we kind of, we're loading in the various parts of the orchestra into more and more complicated models that can ask sort of can help answer deeper questions. So we've looked at examples where we have a single predictor, there's a trajectory that we want to see how it affects an outcome. But very often, especially with my collaborators in women's health, they have multiple hormones that interact in different ways, and they really want to try to understand better how these different hormone trajectories can affect an outcome in a sort of a joint model format so that we can account for one and the other at the same time. So this gets a little messier. I'll just try to hit the high points here. Basically, we now have something that's going to look like a matrix of parameter values based on time. So we have multiple, this is now a vector of multiple predictors. So each one of those predictors is going to have a mean. So there's kind of a column of means here. And then there's now a whole variance-covariance matrix that looks at both the individual variances, which are kind of on the diagonal here, as well as the covariances between these predictors. And our outcome now is going to be a function of this whole matrix of subject level mean predictors, and then the variances and covariances, as well as potentially fixed effects. So so we want to kind of break down piece by piece here. Each one of these beta i's we're going to allow to have its own sort of common mean and variance trajectory. So we're not going to try to share information across the different hormones, but we are going to share information for a given hormone across individuals. And similarly, kind of a log normal for the variance components, for the diagonal parts of the variance covariance matrix. Now, for the covariances, for the associations now between the predictors themselves, so we've actually worked this out in general. That's a little more complicated situation. I'm going to focus on a special case where I just have two predictors. So there's just a single covariance, the sigma 1, 2. And we're going to assume it follows what's called a beta distribution. I don't necessarily, and some of you that do with statistics, you're going to be familiar with this. For those of you that don't, you may not have seen this before. It's essentially kind of a distribution that runs between 0 and 1. Right, so it's for the probability of having some value that's a decimal or a fraction less than 1. And we're doing this little conversion here because this thing can run between -1 and 1. So we're going to add 1 onto it and divide it by 2, so this thing runs between 0 and 1. So we're going to kind of smooth that across. Of course, there's only one of these, right, because there's just a single covariance. So we basically now have, instead of just p mean parameters, we have p times q, right? We have p parameters for each of the predictors, q predictors. And then we have the number of components in the variance covariance matrix, which is basically the number of trajectories times the number of trajectories plus 1 divided by 2. So in the case where q is 2, this is what, 2 times 3, divided by 2 or 3, right? So it's the variance for the first hormone trajectory, the variance for the second hormone trajectory, and the covariance between the two. And then, of course, they have fixed effects. So, I guess I thought I'd switch this up, but I hadn't. Let me go through the example, and I'll come back to the simulation study. So, if there's time, too, I want to leave time for talking. So, so now we're going to be looking at a little different outcome. Before we talked about hot flash, now we're going to talk about change in fat mass. Women during menopause often have a transition between having more fat mass and less lean mass. And we're trying to understand how those may be associated with changes in estradiol as well as changes in FSH. And in particular, we've seen that the declines in estradiol are associated with increased fat mass, whereas FSH has been linked to lower lean mass in postmenopausal women. So, but no real discussion about variance. So now we're going to look at data from SWAN. I mentioned a study at the University of Pennsylvania. This is a study that's nationwide, although one of the key cohorts is at the University of Michigan. These women were a bit older, in their 40s and early 50s, all of them not having reached menopause yet. So these biomarker measurements are collected during baseline and then during annual visits for about 13 years. So it's a little restricted. We ended up with about 840 women that had a final menstrual period known and at least 3 hormone measurements, along with this pre and post pre and post menopause body composition data, with an average of about 12 hormone measurements per woman. So we played the same trick that we did before. We detrended here E2 as well as FSH using a low S curve. It seemed that a linear model in time for both FSH and E2 was sufficient to capture individual level changes relative to the overall trend. And our outcome now is going to be normally distributed. It's going to be this change in fat mass, and we're going to have it be a function. It's actually going to be the change in fat mass divided by the number of years, so it's sort of an annual change in fat mass. Kind of allow for the fact that women had there were different. Some women had longer and shorter, and some had shorter the time periods between the pre-FMP and post-FMP measurement of fat mass. And so we're going to bring in these linear trends for both estradiol and FSH. Right, so there's the intercepts and the slopes. And then we're going to allow for the standard deviation of FSH, estradiol, and then for the covariance of the two to be predictors of this change in fat mass. So to kind of capture what the individual data looks like, we just plotted 4 women at random here. So these little triangles are actually the estradiol measures, and similarly the boxes, the FSH measures. This individual, this line here marks the individual estimate of this linear trend in estradiol for a woman, for a second woman. And then the width of these represents this plus or minus 1.96 times the standard deviation. So you can see how variable these measures are. So it's a little, maybe not entirely obvious, but there is difference here in the width of these intervals that corresponds to differences in the variability in these individual level measures. And finally, the uncertainty around the variability itself, just like we captured the uncertainty of the mean trends with this shaded area, we have these little dotted lines that show some uncertainty in how wide these intervals should be. So those are sort of all the components, the pieces that are going in to predict fat mass. So the actual outcome, so this is just the point estimate and the 95% interval. So we found that both the intercepts of both variables, so sort of the mean level, higher mean levels were associated with greater increases in fat mass. Increases in estradiol were associated with increases in fat mass. And variance in estradiol was associated with increased fat mass. So FSH, in terms of its slope, kind of almost didn't quite make it, but was sort of in the direction we expected. So increases in FSH would be associated with reduced fat mass, or more realistically, smaller increases in fat mass. And similarly for the covariance, some evidence that kind of the stronger the association between estradiol and FSH was associated with less increase in fat mass, although that was a little further away. The variance itself really didn't seem to have a strong effect one way or the other. And then there were some adjustments for ethnicity and race ethnicity, and for physical activity that were kind of in the directions expected. So, okay, so I think I kind of just stated all that in the previous slide. So I think I'm going to skip the simulation study and just wrap this up so maybe we can have a little time for conversation. Basically, things work. So, some open issues. So I think sort of within subject heteroscedasticity, or really changes in variance within an individual over time, would be an interesting thing to take a look at. A lot of examples, I don't think they really had a sufficient number of observations, although I have to say, when I looked at we only kind of recently made this slide. Oops. It occurs to me that there may be some evidence of this sort of higher variability. I should mention the time frame here, everybody's been standardized relative to their FMP. So maybe there's a little more variability around that point in time. We're not totally capturing some of that. So we can investigate that. But in general, I think if you have more observations, you might be in a situation where the changes in variability might itself be reflective of changes in some outcome you're following. And indeed, the outcome could be something like a time-to-event measure, serial analysis, or some kind of time-to-outcome measure would be an important extension. Dealing with missing data. So we've kind of ignored that here. I think MAR is in principle fairly easy to handle, especially in these Bayesian frameworks with imputation. In many settings that might be reasonable, but there may be cases where that's not the case. In sensitivity analysis, there may be some identifiability under certain restrictions. Might be something to consider there. So I've also focused on normal longitudinal predictors and sort of extensions that might allow for that, non-normal, but presumably still continuous outcomes. And so I think there's a lot of potential work to do there. Okay, so I'm going to stop. It was a lot to throw at everybody, I know. So maybe people have thoughts, conversations, questions.